Okay, we're going to finish up our notes on Chapter 2 with one more example of a related rate problem. This has to do with a balloon being inflated. It says that a spherical balloon is inflated at a constant rate of 10 cubic centimeters a second. So the picture is something like this. You have a spherical balloon, and we're pumping air into it, from a hose or something at 10 cubic centimeters a second. So that's how quickly the volume is changing with respect to time. So that's dV dt. It says the balloon will pop once the radius exceeds 20 centimeters. How quickly is the radius of the balloon growing when the balloon pops? So we want to relate the radius to the volume. And if you remember your formulas from geometry, the volume of a sphere is equal to 4/3 pi r cubed. So we're going to use this to relate dV dt to dr dt. So we're given that r will be 20. We're given that r is equal to 20 when the balloon pops, and we know that dV dt is always 10 cubic centimeters a second, and we're looking for dr dt. Okay, so let me apply the derivative with respect to time. So that's ddt. Let's apply that to the equation. V equals 4/3 pi r cubed. And so that gives us that dV dt is 4/3 pi times 3r squared times dr dt. Okay, so the 3's will cancel there. 3/3 cancels. So I'm left with 4 pi r squared dr dt. So dV dt is 4 pi r squared times dr dt. And we're actually looking for dr dt, so let me solve for dr dt by dividing by 4 pi r squared on both sides. So I solve and I get dr dt is equal to dV dt times 1/4 pi r squared. And now I need to plug in dV dt is equal to 10 and r is equal to 20 to figure out what the radius, how quickly the radius is changing when the balloon pops. So dV dt is 10. That'll be cubic centimeters per second, and then I have that 1/4 pi, and then r is 20 centimeters, and we're squaring that. So that is 10/1600 pi, which would be 1/160 pi. So the radius is increasing at a rate of 1/160 pi centimeters a second, which I guess that makes sense, because if the volume is changing at a rate of 10 cubic centimeters per second, the radius is going to be changing much slower, because each additional 10 cubic centimeters doesn't add that much to the length of the radius. Okay, so dr dt is 1/160 times pi centimeters per second. That's the rate of change of the radius when the balloon pops.